Okay, this problem is a little bit complicated because it deals not only with centripetal acceleration, but also with a ramp. So drawing this means we have to draw it in 3 dimensions, which I'm not very good at, so I'm going to draw it in maybe 2 different 2-dimensional problems. It says a circular freeway entrance and exit ramp are commonly banked to handle a car moving at 30 miles an hour, 13 meters per second. To design a similar ramp for something twice the speed, what should we do? Should we increase the radius, decrease the radius, and by what factor? And the little square root part on this problem didn't show up. So it's by 2, 4, or square root of 2. So let's look at this problem and see what we're getting at. So we have some banked curve. We have our little car. It's got its little wheels, and it's going, I'm going to say, going into the page with some velocity. This is my velocity 1. And it's going to have some radius of curvature. We want to know how much does my radius change when I go to a different velocity. Well, in order for me to solve this, I need to figure out what are my forces that cause me to do centripetal acceleration. And it says that the car is designed to handle cars moving at that, which is a way of saying that the friction force is equal to 0. We don't want to use friction because if the roads are icy or wet, then we might slide. So we want this bank curve to naturally let us do a 30-mile-an-hour spin or a 60-mile-an-hour, depending on which one we're designing. So I'm going to draw my free body diagram. My free body diagram for this says that I have a normal force pointing perpendicular to the ramp. I have a weight force pointing straight down from the ramp. And I don't think I have any other forces. There's no upward forces, downward forces, no friction. So here's the trick on these problems. The trick is to set up a coordinate system that works for you. And I know that if you've done a lot of banked curve problems, or problems, not banked curve, but just ramp problems that you normally want to do a shifted or a tilted coordinate system, I'm actually going to choose the x to be towards the center of our system and y to be vertical. So almost a standard coordinate system. It means that my weight force is in the y direction only, but my normal force in this case is going to be in the x and the y. So it's going to be a little bit involved, but we know Newton's second law says that mass times our net force is going to give us an acceleration. So I'm going to look in both the x and the y direction. So in the x direction, I'm going to see that I have a positive normal force, and I need to know what angle it's at, because I need to know what trig function I'm using. So I'm going to put in here a couple different dotted lines just to give me some geometry. So I know that I gave myself theta here, which means that this angle is theta, which means that angle is theta. So this angle right here is theta because of complement angles and triangles having 180 degrees in them. So I need the x component of this, which is going to be sine of theta. My x component is going to be my opposite, so I'm using the SO part of SOHCAHTOA. All right, I need to know if there's any other forces in the x direction. In the horizontal direction, I got normal force. My only other force is a weight force. It's only in the y direction. So this is what's going to provide my centripetal acceleration in towards a circle. And that's actually why I chose this coordinate system is because I wanted the acceleration, the centripetal acceleration, to be only in one dimension. Just makes life easy. So we have n sine theta is equal to m v squared over r. The bad part is I don't know what n is. I want to know the relationship between v and r, but I don't know if I change r or v, if n is going to change. So I got to check to see what my n is. So if I look in the vertical direction, I get that my normal force times the cosine of the angle minus the weight force gives me 0. Normal force perpendicular upward minus the weight force downward gives me this, which means n is equal to mg over cosine of theta, which means my normal force is only determined by my weight force and my angle. In this problem, my angle doesn't change. So if I were to figure out a relationship between r and v, I'm going to draw it over here. I'm going to just start to substitute in. So I got mg over cosine of theta times sine of theta is equal to mv squared over r. M cancels with an m, so I get r times g sine over cosine is tangent of theta. G tangent of theta equals v squared. So if I double my velocity, if I put in a factor of 2 here, my radius is going to get a factor of 4. 2 squared is 4. So I need to increase my radius. So increase my radius, and I need to do it by a factor of 4, because 2 squared is equal to 4. So not that difficult of a problem. It took a little work to get there. We had to do a couple different Newton's second law problems, one in the x, one in the y. And I think the trick on this one is to choose a coordinate system where one of your dimensions, one of your directions, in my case, x direction, was solely in the same direction as my centripetal acceleration. It makes life a whole lot easier to solve.